jumping robot, origami robot, and the soft wearable robot called Exoglory. The work on the water jumping robot was published in the Science and covered by over 300 news media worldwide. The aspect. Okay, so please.
Okay, thank you very much. This is a great honor to be here and give a talk at IROS. Today I'll give you a talk about soft robotics, but today I'm not going to be telling you about technical details too much about my work, but I want to provoke you about what soft robotics is and how should we design better soft robots. And I chose the word physically embodied intelligence because I think it somehow could be a principle of creating motion with soft robots. I've been at SNU for 10 years now, and 10 years ago when I joined SNU, I said I'm going to build new type of robots. I didn't know what they were going to be, but I said I'll be using new type of materials, new manufacturing style. I'll be doing like bio-inspired design. And we've been building many different types of robots. But at one point, after like 3-4 years, our students were asking me, what kind of robots are we building? What is this? And the word soft robotics, thanks to our soft robotics community led by Cecilia, Professor Cecilia, asking many people, we were able to find the identity. Oh, we are doing soft robots. But what is a soft robot? And what's the principle behind soft robots? And I've been asking that question, and that's when I met Professor Ron Piper. He's been talking about soft robots and robots with embodied intelligence. He has written a very famous book, How the Body Shapes the Way We Think, talks about embodied intelligence, and also later in 2013, he also edited a book about outlooks of morphological computation. And also Fumiya Ida also wrote many papers about soft robotics and morphological computation. So if you're interested, you should read those papers. And also Meticity named his department Physical Intelligence. And also just this year, Professor Elliot Hawks and Mark Bukowski wrote a review paper about design of materials and mechanisms for positive responsive robots. And all these talks, all these concepts, they are talking about reducing the cost of computation and control using design, using morphological design. And this is a figure from Ron Piper's book about embodied intelligence, and he says the behavior is not the outcome of an internal control structure only. Computation is outsourced to body morphology and material properties. And one good example is Boston Dynamics Rex. And as you can see, this robot, instead of sensing and controlling because of its morphology and fast legs, it can overcome this kind of rugged terrains very well. So this type of example is what morphological computation, embodied intelligence is given to us. So back to the basics, how is a motion created? Motion, when you think about it, you have a body, you have a kinematic design, linkages, formal linkages, and then you attach an actuator. That's how you create a motion. Hard robotics, there's no word hard robotics, right? But why not? If there's soft robotics, there should be hard robotics. So if you think about hard robotics, there is a definite difference between parts that does not deform at all, and there are joints that creates motion. So you have a clear distinction between where the part moves and where the part does not. And because of this clear distinction, you can do an analytical modeling of these robots, and also you can do control and everything. How about soft robotics? I'm sure soft. What is the kinematics of a soft robot? It has infinite degrees of freedom. How do you create motion with this kind of soft material? What's the principle? How should we design this? That's the question that we had. For example, joint for hard robots. We have regular joints, prismatic joints. We have this set of joints that we can use to create motion. We attach linkages to these joints and we can create new mechanisms. How about soft robots? What's a joint? Is it distributed joint in continuum space? What is it? So this question has been like startling me for quite some time. But we've been building robots without really understanding what it is. I don't think we still fully understand what soft robot is, but I think we are trying to go there. So I'm gonna give you a very simple example. Imagine a single degrees of freedom joint. And imagine this graph is the energy that is required to create motion. So for this kind of single degrees of freedom joint, this portion, because this is perfectly rigid, to deform this, you will have a very high energy, required energy to create motion in this part. This joint can easily create motion. This part, again, is really hard to create motion. Imagine a notch beam. Think of this as a sample soft robot. If you have this kind of notched beam, soft material notched beam, if you think about the required energy to create motion, this portion will have higher required energy, whereas this portion will have lower required energy and back, right? What's the degrees of freedom of this kind of beam? But you already know that this portion will create the largest motion. So that's where the minimum energy is. So the motion will go through the minimum energy path. So I argue that for soft robotics, kinematics is closely related with minimum energy path. And if you design a minimum energy path, you can design a morphological behavior. So you can create this kind of energy map, and this will have a certain minimum energy path. So if you design this minimum energy path in new ways, you can create new type of soft robots. Kinematics, well, how do you create this kind of kinematics of soft robots? Imagine very simple soft sheet. And if you do this to, for example, a towel, we're gonna create a certain motion. Every time, if you do this with the exact same force, exact same motion, and nothing changes, you're gonna get the exact same kinematics, right? But if you design an energy barrier to a movement, so if you put some rigid surfaces onto this sheet and you do the same motion, you're gonna get a different kinematics, right? So, the Harvard's NewNet design, this design actually basically follows the minimum energy path of deformation. So, the way this moves is there's a body design and there's an actuator input, and it basically follows the minimum energy path for this motion. So how do you design a minimum energy path? Basically, it's patterning. You do patterning of soft material. If you do this patterning, you will be able to create different motions. So if you can actually even wind the tendons around soft material, that will constrain, and it's going to have a different minimum energy path. And you're going to get different motion. Again, same thing with this kind of Harvard motion. And motion is generated by elongation of soft materials. So I argue that if you understand this really well, you can create different types of motions. For example, one approach that we are trying right now is dual morphing. So on top of this elongation-based soft material motion, we are trying to add a folding pattern. Folding has a different minimum energy path, and even if you still have the same pneumatics going in, you're going to have a totally different motion, which is a rotation by the facets connected to creases. So if you combine these two, you're going to get dual morphing. You're going to get a deployment as well as expansion, elongation-based motion. So you can create something like this, soft robotic. We call it soft robotic origami because it has the idea of origami embedded with soft robotics. And as you can see, you can create this kind of large deployed motion plus elongated motions. But what's more interesting is start with the same block, but depending on how you design this material, you can get either this kind of motion, this kind of motion, this kind of motion. just depending on how you design your material. So each one has different minimum energy path. And because it has all different minimum energy path, you get all different end effector trajectory, even if you are starting from the same shape. So what can you do with this kind of design? You can deploy a soft robotic crawler, you can do soft gripper, something that can grip the ball and keep it safe. You can do something like this, something that is stored and then expands, and we can use that for catching crawling robots. Maybe we can do Baymax. If you know Big Hero, actually Baymax starts flat and then it expands to become the Big Hero, the Baymax. So we can do something like that as well. So we were able to do this kind of design by designing a new minimum energy path. Another way of designing minimum energy path is by stiffness patterning, inspired by origami. We've been working on this for quite some time. And it all began with this robot, actually. Back about 7 years ago, we wanted a soft robotic wheel that could change its shape. So we designed this kind of robot, all made with shape memory alloy actuators. And it was able to change its wheel shape and go under, and it could change its shape to go over that. Problem was, it's too complicated. It had 16 shape memory alloy actuators. The students hated it. If one of them breaks, you have to do everything. So we had to think about, can we simplify this design? How do we simplify? That's when we came up with the idea of combining origami concept. So you start with your soft material with high degrees of freedom. You structure them, you pattern them with folding patterns. You can imagine by folding, you're changing the minimum energy path. And if you do that, you are embedding new mechanical properties into the material. And it's a way to apply the structural characteristics to material. So we started designing wheels. So you start with high UF structure, and you replace facets, rigid facets, and it's going to be creating new minimum energy path. And we actually manufactured this using fabric and facets. And we were able to create this kind of robot. We changed the shape of the wheel with a single motor, just one motor. But as you can see this kind of large change of the shape of the wheel. And when the wheel is large, it can go up the stairs. And when the wheel becomes small, it can go under narrow gaps. It's adaptive to the environment. You can adapt your robot to the environment by doing this kind of transformation and shape changing. And probably, if you have many of these robots that can go into disaster areas, maybe you can do something like this, find some people who are in need. So we built a bigger version of this to go to the Soft Robotics Challenge hosted by Pisa, Italy's Spiria Santana. And as you can see, we had this robot that could change the wheel. And one thing that we noticed was because the wheel is really lightweight, but it can carry a large load because of the perpendicularity of the shape of the wheel. And we came up with an idea of using that concept for arm of a drone. Drone, it's very sensitive to weight, so you need very lightweight arm. And if it can change its shape, that would be really nice. It can become long. And another important thing is that it has to be rigid when it's elongated. So we designed this kind of robot based on our origami patterning. And one interesting point is that it's very lightweight, 28 grams, but it can carry a weight of 12 kilograms. So you can see that it has a very high energy required to deform, at least in this state. But by designing the patterns and the path, tandem path correctly, we can actually change the shape of this structure really easily. Really easily in this. Changing the shape is really easy with a single tandem path, but it resists the external force. So that's how we design the energy profile. So I said by designing a minimum energy path, we can design morphological behavior. Basically, we are designing the kinematics. But if you think about designing an energy plane, then we can actually design the characteristics of actuation and response. What do I mean by that? So I said there is a minimum energy path, but this minimum energy path could be linearly increasing, but it could be very nonlinear. It could go flat and then it could drop quickly, it could go up, and what can we do with that? Energy slope determines the dynamics and stability of the movement. For example, so this, and also, whenever there's an unwanted deformation, we say hard robots, they don't respond, but soft robots, they respond because it's about energy, right? There's a minimum energy path. That's the desired kinematics. But even though when there's an unwanted external force, then we will have this kind of unwanted deformation, which is good for adaptiveness. It will adapt to the environment very well. So for example, fly trap. Fly trap's motion is interesting because it closes its leaves in a very quick manner. And the principle behind this is bistability. Bistable structure enables this kind of creation. And we can do the same in engineering by using unsymmetrically laminated carbon fiber. So we can create this kind of fly trap inspired structure. Oops. We can create this kind of structure. And as you can see, it has a bistable property, so it flips. And when it flips, it snaps really quickly. We were able to build one out of polymers, the same principle, unsymmetrically laminated, and it's going to create this kind of motion. So it's going through the minimum energy path, but the path, it's not just linear, but it has this kind of slopes, which creates this kind of dynamics. So you can actually put fluid into it, and you can actuate this kind of shape. We are also building this kind of flat shape, which we call an origami morphing pattern. It's changing shape from flat to three-dimensional structure, but as you can see, when it changes, it's bistable. So it's very stable at the end state, and it snaps, it sort of snaps instead of just doing a linear motion. And this was done by designing the minimum energy path in a special way. Another interesting thing is water strider jumping on water. Water strider can actually jump on water. Water is a very, very fragile environment. And in order to jump, you need to apply a large force. But it still manages to jump on water. How do they do it? The important criteria for water strider is that you should not go above certain force. That's surface tension. If you go above surface tension, the water is going to break. No more surface tension, and you're not going to be able to jump. The problem of jumping mechanisms is that we've been using escape CAM mechanism, which stores energy and releases them at once. Boom. It can work on ground, it's not going to work on water. So, inspired by Flea's mechanism, we use torque reversal mechanism. This torque reversal mechanism, this is a single joint, but because of how the actuators are placed, what happens is this is an extensor muscle, which actually extends, but at this state, it's not extending. But by pulling this extensor muscle, actually it changes the direction of the torque, and it starts to open up. one important thing is movement arm is changing. So at this state, you have a very small movement arm, but you have a very large force. At this state, you have a very large movement arm, small force, which allows us to sort of limit the maximum force, but still be able to have the same momentum. So by this kind of design of a force profile, we were able to jump on this fragile water. And we created a very small version with the same basic principle, and we were able to create something that could actually jump on water. We also designed a gripper based on buckling. So what we found was if we use the buckling phenomenon, instead of having this kind of linear property, this force increases, but when there's a flexure buckling occurring, this kind of phenomenon happens. Even though the gripping angle changes, the force is the same, which is really good for adaptive gripping when you have multiple of these spikes. So by designing this kind of energy profile, we were able to get a very adaptive recipe. And also we were able to create a passive origami-inspired continuous variable transmission together with Harvard group with Sam Felton. This doesn't have an actuator, but it responds to the external load. So imagine a rigid wheel. When it's small, it can carry large load. But if the wheel is too big, it cannot carry large load. But our wheel can respond to the load. And when there is a large load, it changes its shape. And that's how it can pull that kind of large load. So those were some of the examples that I chose from the research that I've been doing. And I say that the kinematics of soft robotics can be designed by designing a minimum energy path. And by doing that, you can design your morphological behavior. And also, not just this path, but looking at other directions. If you can change, you can design the whole energy plane, then you can actually design the actuation and the response. So this energy landscape design is very useful for creating desired motion. And as I showed you with the dual-morphing example, if you explore this, we have a very large design space to explore, and we'll be able to create new type of robots. And that's why I use the term physical embodied intelligence, because I think it has a meaning. But to tell the truth, the way I'm using this physical embodied intelligence is somewhat different from most of the other people, because we are using this embodied intelligence for actuation, where most of the time we talk about sensing and control. But I believe that they are very related. Actuation and response, they're basically responding to a force. It could be an actuation force, it could be external force. It's all about designing this energy plane. So if you have this kind of very nice energy plane, and I believe you can, is a hard robot really a hard robot? We assume it's a hard robot. We assume everything is rigid, but nothing is perfectly rigid. So if you try to understand that kind of structure with this design, for robotic arm, this direction is this is the minimum energy path. But if you apply force in this direction, it could move, right? There could be a minimum energy path. So I think trying to understand soft robotics using this kind of energy plane will give us a lot more freedom of design, and we can come up with very new designs with this. So I'd like to thank my students. Without my students, I would have all these kind of research that I've done. And I have one announcement to make. RoboSoft 2019 is happening in Seoul, Korea, and next April. RAL Robosoft submission should be open today. It's due in 2 weeks. So start writing your RAL Robosoft papers. The conference submission is November 1st. We'll be doing it at the COEX, which is the biggest convention center in Korea. It's at the center of Gangnam. And you can actually see the statue of Gangnam Style at our meeting room. So if you're really interested, submit your paper, come to Robosoft. Thank you very much.